track communication interfaces with other systems in IPF implementation, ensuring integrity while enabling necessary integration. Instrument Protective Functions IPFs are designed to operate autonomously, yet they rarely exist in complete isolation. In a modern facility, IPFs often need to communicate with other systems, such as the Basic Process Control System, BPCS, Emergency Shutdown Systems, ESD, Fire and Gas Systems, FGS, Alarm Management Platforms, and Asset Management Systems for visibility, coordination, diagnostics, and event logging. However, this communication must be managed with strict boundaries to ensure that integration does not compromise the independence, reliability, or safety integrity level SIL of the IPF. Interfaces must be carefully defined, validated, and secured to maintain both operational functionality and safety performance. Principles for safe communication integration. One-way data flow from IPF to other systems. IPFs may transmit status, alarm, and diagnostic data to external systems, but external systems must not have the ability to modify IPF logic, parameters, or bypasses. Read-only integration preserves visibility without risk of interference. Functional independence must be maintained. Communication must not create logical or physical dependencies between the IPF and non-safety systems. IPFs must remain capable of executing their safety function independently of the availability or correctness of external systems. Clear data ownership and interface definition. Every communication pathway must be documented in interface control documents, ICDs, including signal direction, data type, purpose, and failure behavior. Ownership of each data element, whether from the IPF, BPCS, or utility systems, must be clearly assigned and controlled. Common IPF communication use cases. BPCS integration allows operators to monitor IPF status, receive trip alarms, and view bypass conditions through standard operator consoles. No control or logic modification is permitted via the BPCS interface. Fire and gas system FGS coordination. In some cases, FGS signals may trigger IPFs or be triggered by IPF activation, e.g., coordinated blowdown or shutdown. These integrations must be designed using hardwired or safety-rated communication protocols and tested for deterministic behavior. Asset management systems. Diagnostic and maintenance data from IPF components, e.g. smart transmitters, valve positioners, may be communicated via HART or field bus protocols for condition monitoring and maintenance planning. These communication paths must not interfere with the real-time safety function. Alarm and event logging platforms. IPF events, trips, bypass activations, and diagnostics should be logged and time-synchronized across systems to support incident investigation and compliance reporting. Logs must reflect both process values and safety system decisions. Approved protocols and network considerations. Safety-certified protocols for critical links. When communication is part of the IPF logic, e.g. distributed logic solvers, only safety-rated protocols, such as ProfiSafe, SafetyNet, or SIL-rated Modbus variants, may be used. Segregated networks for safety systems. Safety networks must be physically or logically segregated from control and business networks. Firewalls, data diodes, or unidirectional gateways must be used to enforce separation and prevent unauthorized access. Latency and determinism. For time-sensitive functions, communication delays must be accounted for. Non-deterministic or delayed systems, e.g., wireless Ethernet without QoS, may not be suitable for SIL-rated interaction. Testing and validation of interfaces. Interface testing during commissioning. All communication links must be functionally tested to confirm expected behavior under normal, fault, and degraded conditions. Failure mode evaluation. Systems must be assessed for communication loss, corrupted data, and unexpected responses, ensuring that the IPF always fails safe. Ongoing monitoring and change control. Any modification to communication mappings, protocols, or connected systems must be subject to formal management of change, MOC, processes with revalidation of safety impact. Conclusion. Controlled integration without compromising protection. While communication between IPFs and other systems is often necessary for visibility and coordination, it must be designed with clear boundaries and robust safeguards. Communication should serve the function, not influence it. By adhering to strict interface design, tested protocols, and documented integration strategies, facilities can ensure that IPFs remain functionally independent and reliably protective, while still providing the operational transparency needed for safe and efficient plant operation. Maintenance overrides in IPF implementation. Balancing maintenance flexibility with safety assurance. Maintenance overrides, also referred to as bypasses, inhibit commands, or force signals, are temporary measures used to disable or suspend an instrument protective function, IPF, or one of its components during testing, calibration, or corrective maintenance. While overrides are sometimes necessary for safe and efficient maintenance, they also introduce risk by reducing or eliminating a critical layer of protection. To maintain safety integrity, all maintenance overrides must be applied, controlled, and removed under strict procedural governance. The use of overrides must be treated as an exception, not a routine action, with clear authorization, traceability, and compensating measures. Principles for safe use of maintenance overrides. Formal authorization process. Overrides may only be applied by authorized personnel and must be approved through a documented process. The reason for the override, affected IPF, duration, and responsible individuals must be recorded before implementation. Time-bound and revocable. Overrides must be applied for the shortest duration necessary. They must be automatically removed after the defined period or manually revoked after task completion, with confirmation that the IPF is fully restored. Visible indication on operator and engineering interfaces. Active overrides must be clearly and persistently displayed on the operator HMI, safety system diagnostics, and event logs. The display should indicate which function is overridden, for how long, and what action is being taken to mitigate associated risks. Types of maintenance overrides. Signal simulation or forcing, used to simulate sensor values or final element feedback during functional testing. Must be tightly controlled to prevent false logic activation or masking of true conditions. Bypass of logic conditions, temporarily disables specific trip paths or interlocks. Requires logic solver access, engineering approval, and defined fallback procedures. Mechanical or physical isolation. Examples include blocked valves, removed actuators, or disabled power supplies. These must be supported by lockout-tagout, LOTO procedures, and physical signage in the field. Compensating measures during override period. To preserve overall risk tolerability while an IPF is disabled, one or more of the following must be implemented: increased operator surveillance or field monitoring, temporary activation of alternative protection measures, e.g. alarms with manual response, reduced process throughput or derated operations, administrative controls and heightened readiness to respond to deviations. If no effective compensating measure can be applied, the process or unit must be placed in a safe condition until the IPF is restored. Documentation and audit requirements. Override logs. Every override event must be logged with date, time, reason, personnel involved, and restoration confirmation. Integration into safety lifecycle records. Override history must be reviewed during periodic safety audits, proof test analysis, and performance reviews to assess patterns and potential design weaknesses. Post-override verification. Upon completion of maintenance, a full function check must be performed to confirm that the IPF has been returned to its fully operational state. Conclusion: overrides are a controlled deviation, not a default practice. Maintenance overrides are necessary tools for sustaining and servicing safety systems, but they must be applied with discipline and transparency. Poorly controlled overrides are one of the most common root causes of safety incidents involving otherwise functional IPFs. By treating each override as a formal, auditable exception, with clearly defined procedures, compensating measures, and restoration verification, facilities can maintain protection even during moments of planned vulnerability. Operational considerations for maintenance overrides. Maintaining situational awareness and control during temporary IPF disablement. From an operational perspective, maintenance overrides introduce a temporary but significant shift in the plant's risk profile. While necessary for inspection, calibration, or troubleshooting, overrides reduce the facility's protective layers, placing greater responsibility on operations personnel to monitor the process and manage any deviations manually. As such, operational considerations must focus on awareness, coordination, and readiness to act during the override period. Operators must not only be aware of which instrument protective functions IPFs are affected, but also understand the consequences of their temporary unavailability and the steps required to maintain safety during that time. Clear and persistent operator notification. Visual indicators on the HMI. All active overrides must be clearly shown on the operator interface with unambiguous labeling. Each notification must include the IPF tag, function name, start time, responsible party, and expected restoration time. Audible or pop-up alerts for new overrides. When a new override is applied, operators should be immediately alerted through a distinct audible or screen notification requiring acknowledgement. Status display in central overview screens. A summary of all active overrides should be available on process overview pages, not buried in submenu navigation. Procedural alignment with operations. Pre-override briefing. Prior to applying an override, operations and maintenance teams must jointly review the purpose, process impact, required compensating measures, and escalation plan. Defined operating constraints. Depending on the risk, operations may be required to implement temporary limits, e.g., reduced feed rates, pressure thresholds, or flow caps until the IPF is re-enabled. Manual intervention readiness. Operators must be trained and prepared to take manual action, e.g., shutting a valve, stopping a pump, should the protected parameter approach critical levels while the IPF is out of service. Coordination and handover requirements. Shift handover awareness. Any active overrides must be explicitly communicated during shift handover with acknowledgement by incoming operators. Override logs should be integrated into shift reports and standing instructions. Cross-discipline communication. Operations, instrumentation, safety, and control system teams must maintain continuous coordination throughout the override period, especially if troubleshooting activities are underway. Post-maintenance reinstatement and function check. Restoration, confirmed by both maintenance and operations. After maintenance is completed, both the responsible technician and control room operator must confirm the override has been removed and the IPF is restored to normal function. Operational verification prior to restart or load increase. Where the IPF is critical to safe startup or high-rate operations, its functionality must be verified before returning the unit to full service. Human factors and interface clarity. Avoid ambiguous override states. The interface must clearly differentiate between a normal trip condition, a fault, and a manual override. Misinterpretation could result in unsafe assumptions. Minimize override duration. Operators should track override timers and escalate if planned restoration deadlines are exceeded. Overrides must never be allowed to become the new normal. Conclusion: operational discipline is critical during override periods. While maintenance overrides are technical tools, their safety impact is managed through operational discipline. Operators are the frontline defense during periods of protection loss. By ensuring awareness, defining compensatory procedures, and reinforcing interdepartmental coordination, the risk introduced by overrides can be effectively contained. In this way, operational readiness becomes the temporary stand-in for automated protection until the IPF is safely restored. The Automatic Maintenance Override Switch, automatic MOS, enabling safe, controlled bypass for routine maintenance activities. The Automatic Maintenance Override Switch, automatic MOS, is a purpose-built feature that allows predefined parts of an instrument protective function, IPF, to be temporarily overridden through a controlled, automated mechanism, typically via logic configured within the Safety Instrumented System, SIS. This functionality is designed to support scheduled testing, calibration, or maintenance tasks while minimizing the risk of accidental trips, unsafe bypasses, or loss of protection. Unlike manual overrides, which are initiated case by case, an automatic MOS is predefined, pre-validated, and embedded into the system logic. It ensures consistency, traceability, and safer execution of routine interventions on critical IPFs. Purpose and benefits of an automatic MOS. Structured override for test and maintenance procedures. Enables testing of sensors or final elements without triggering a full process shutdown or false trip condition. Supports safe simulation of inputs and actuator movement while preserving control over logic execution. Reduces operator error. Automated override logic eliminates the risk of improperly applied manual bypasses or forgotten resets. Built-in conditions and timers guide users through the override and restoration sequence. Embedded safety checks. Logic may include permissive conditions, e.g., process in safe state, no active demand, to ensure the override is applied only when appropriate. Typical features of an automatic MOS. Predefined scope. Only specific designated IPFs or components, e.g., one transmitter in a 203 sensor voting group, are eligible for automatic override. The MOS cannot be arbitrarily extended to other functions or hardware without revalidation. Time-limited activation. Automatically expires after a preset duration to prevent indefinite bypass conditions. Configurable timers ensure the override window is long enough for task completion, but not unnecessarily extended. Restoration enforcement. System logic ensures the IPF cannot return to normal service until a function check is completed and all override conditions are cleared. Restoration may be confirmed through operator acknowledgement or diagnostic validation. Status indication and alarming. Active MOS states are clearly displayed on the operator HMI and maintenance interface with associated alarms or alerts. Logs include user identity, time of activation, affected function, and return to service confirmation. Design and implementation considerations. Predefined in Safety Requirement Specification, SRS, the use of automatic MOS must be described and justified in the SRS, including allowed scenarios, logic structure, and constraints. Risk-based justification. Justification for each automatic MOS must demonstrate that the temporary loss of protection is either tolerable or offset by compensating measures. In SIL-rated functions, the impact of the MOS must be included in availability and PFDAVG calculations where applicable. Access control and role separation. Only authorized maintenance personnel may activate an automatic MOS, typically via secure engineering interface or key-operated switch. Operations must have visibility but not control unless explicitly approved. Limitations and cautions. Not a substitute for MOC or safety assessment. Automatic MOS should only be applied for well-understood recurring tasks. Unusual or complex override scenarios must still follow formal management of change processes. No overlapping overrides. Systems should prevent activation of multiple overlapping MOS conditions that could compromise functional independence or reduce voting group effectiveness below safe limits. Ongoing validation required. Automatic MOS logic must be tested during factory and site acceptance testing and revalidated during system upgrades or safety audits. Conclusion: the automatic MOS enables repeatable, safer maintenance. The automatic maintenance override switch provides a structured, automated mechanism for managing routine IPF interventions. When properly designed and governed, it allows critical maintenance and testing to proceed without compromising safety or creating uncontrolled bypass risks. By embedding logic, time constraints, and clear visibility into the override process, the automatic MOS becomes a disciplined tool, ensuring maintenance flexibility while preserving system integrity and regulatory confidence.